Thank you, Lars, for that generous introduction. So I'm going to be talking about black holes and gravitational waves, and the punchline will be, was Einstein right? And there's no suspense. Yeah. No. You can leave now if you the rest is details, right? So this is actually a very special time in physics, because it's almost exactly 100 years since the publication of this paper by Albert Einstein. If you look, you'll see the date, November 2015. And if you don't read German, it says the field equations of gravitation. And it was in this paper that Einstein finally, after a long struggle, came to the correct equations for the new theory that was going to replace Newton's theory of gravity. This theory, among other things, made two very unusual predictions. One of them was that there should be gravitational waves, and I'll explain in a little bit what that means. And Einstein himself realized that pretty soon after he did this work. And the other prediction, which came much more slowly, and in fact, it was a prediction that Einstein himself never really accepted, was that this theory predicts the existence of black holes. And so I'll describe a little bit about that as well. And then what we will come to in the end is the climax, which was announced just last year, was the discovery of gravitational waves that came from the merger of two black holes. So the whole thing coming together 100 years after this theory was proposed. All right, so let's start with what is a black hole. So suppose I take my keys and I throw them up in the air. Okay, we all know they go up and then they stop and then they fall down. And the more speed I give the keys when I launch them, the higher they go before they fall back. If I could throw the keys at 25,000 miles per hour, we're theorists, right? That's what we do. We do thought experiments. But if I could throw the keys at 25,000 miles per hour, they would never fall back. 25,000 miles per hour is the escape velocity from the gravitational field of the Earth. Now suppose I could somehow take the Earth and squeeze it down till it was about that size, the size of a golf ball. Now, you probably know from Newton's theory of gravity that the strength of the gravitational force depends upon the distance that you are. If you keep the mass of the Earth fixed, and you squeeze all of its matter down to that big, and you're still on the surface trying to throw your keys up in the air, your distance from every other part of the Earth is much smaller. So the Earth's gravity has gotten much stronger. And in fact, when the Earth is about that big, the escape velocity becomes equal to the speed of light. Since nothing can go faster than the speed of light, if I try to throw my keys up, there would be no speed I could throw them at that they would leave. The keys and me would be trapped by the gravitational field of the Earth. We will have turned the Earth into a black hole. So basically, the answer to the question, what is a black hole? A black hole is a region of space and time from which nothing, not even light, can escape. Okay, so that's the prediction. Now, of course, I could never assemble, or nature could, it would be practically impossible to take the Earth and squeeze it down. So how does nature actually make black holes? Well, nature uses gravity itself. So what we believe is that if you have a massive star, say maybe 40 times the mass of the sun, it supports itself against its enormous self-gravitational attraction by burning nuclear fuel, by having nuclear reactions in its core. And the pressure provided by all that heat holds the star up. But when you've used up all of that nuclear fuel, when there's no more nuclear reactions that can take place, then the pressure diminishes and the star will start contracting under its own gravity. And eventually there's an implosion, and the core of the star goes all the way to make a black hole. So that's how we believe the simplest way to make a black hole. Okay, so general relativity was this bizarre idea of Einstein's that instead of thinking of gravity as a force, as Newton proposed, rather it's described by a warping, a curvature of space and time, changing the very geometry of space and time, depending how the matter and energy is distributed. And so the equations that Einstein wrote down in that paper were extremely complicated, very difficult to understand what all the predictions were, let alone to try to solve the equations for some complicated astrophysical situation. We're still learning new things about what the theory tells us. And as computers have become more powerful, there's been a new subfield of astrophysics called numerical relativity, which basically says, okay, I give up. I'm not smart enough to solve these equations with pencil and paper. I'm going to cheat and use a nice big computer and put the equations on the computer and figure out what the theory actually predicts. Now, this idea of solving complicated physical problems on a computer, it's sometimes called doing a simulation. I don't like the word simulation because it suggests that it's something not quite, there's a bit of pretense involved. So I'll try to use the word just a computation. You really are computing what the theory tells you about. So the objects we're going to be interested in, first of all, a black hole. So a black hole has a surface, and of course surface is too mundane a word, so we'll call it a horizon just to make it sound like we're, a bit of a priesthood. And there are these bizarre properties. Space is warped. The geometry here is not Euclidean geometry. Time slows down near the horizon of a black hole. That might sound strange for you. How can time be affected by gravity? Well, that's one of the predictions of Einstein's theory. And you might say, well, maybe you guys are predicting it, but of course it's not true. Well, any of you who use your phones for GPS, you know how GPS works? There are a bunch of satellites, about 24 satellites orbiting around in 12-hour orbits around the Earth. At any moment, there are about 3 or 4 of them that are up in the sky above us. On these satellites are very precise clocks. And the orbits of the satellites are tracked very precisely, so we know at all times exactly where the satellites are relative to the Earth. These satellites send out signals down to the ground, which encode the time at which that signal left the satellite and the location that the satellite was at when the signal left. My phone receives those signals. It has a little computer inside and also a clock, very accurately calibrated clock. And so it takes those times, and it can take the difference between when the signal left and when it arrived. We know the speed of light, so it can figure out the distance to that satellite. So we know the distance to some fixed point. And if you have enough of them, you can just do high school trigonometry, and you can figure out where you are. Okay? So that's how. That's easy, yeah. There's one little snag. That satellite is moving at about, I don't know, 18,000 miles per hour or something like that. And according to Einstein, moving clocks run slow. So you have to put in a little correction for the fact that the ticking rate of that clock, the timekeeping of that clock is different from my clock down here on the Earth. Also, that clock is high up above the Earth. It's further from the center of the Earth, so the gravity of the Earth is weaker up there than it is here. And so, once again, that clock runs a little faster compared with the clock down here. These effects are very, very tiny. But because the speed of light is so big, when you multiply that in, you get a measurable effect. And in fact, if the software for GPS did not include the corrections for general relativity, the whole system would break down in about 20 minutes. The errors would be many miles. It would be useless. So the stuff is real. Okay, so the interesting objects from the point of view of someone who's studying strong gravitational fields, we've already mentioned the black hole. Black holes also have a property besides having a mass, which can produce gravity. They can have a spin, an angular momentum. And this angular momentum can, I try to show it with these arrows going around, can drag space around in it, a purely gravitational effect that is not part of Newton's theory. The other interesting object made out of pure gravity is a gravitational wave. So what's a gravitational wave? Well, imagine you drop a pebble into a pond, right? You see the ripples going out, the little water waves. You can think of a gravitational wave like a ripple, but it's a ripple of the curvature, the warpage of space and time. And it propagates outward at the speed of light. And up until now, this again has been a purely theoretical prediction. Another strong gravity object that I'm not going to talk much about tonight is a neutron star. If you start with one of these giant stars that collapses, and if it doesn't quite have enough mass to push it all the way to a black hole, it can end up with a core which is a neutron star, an extremely dense object. It's an object about, say, the mass of the sun, but about the diameter of Santa Barbara, roughly. Okay, not counting Montecito. Yeah, I hear some knowing laughs from there, but anyway. Okay, so I'm not going to talk much about those, except to say that if we make a census of what do we actually know, what have we actually observed, and what do we understand, so neutron stars just kind of sitting there minding their own business, we understand them pretty well, and they've been observed. We observe them, among other ways, as radio pulsars. We see pulsed radio signals coming from them. Quiescent black holes, they're understood. That's one of the rare cases where we can actually solve Einstein's equations with pencil and paper and describe the geometry completely. And observed, I'm going to put no with a question mark. Right? And I'll come back to that. Wildly dynamical black holes are partially understood, as I'll explain. And the big discovery of last year is, yes, they've been observed. Wildly dynamic neutron stars, so here's a little picture meant to represent a neutron star being torn apart as it plunges into a black hole. These are not really understood theoretically. I mean, we're part of the work that we're doing right now is trying to calculate these things on big computers, and not yet observed, but we're expecting big things from the experiment maybe in the next 2 to 3 years. We're hopeful to actually detect these. All right, so why the question mark back here? Well, you may have read in the newspaper, black hole discovered, in some galaxy or other. There's even a black hole in the center of our own galaxy, according to the, astronomers. Well, what the observations actually tell us is there are regions in the universe that have a lot of mass in a small volume. If general relativity is the correct theory of gravity, then these have to be black holes. But we don't have any independent measurement that tells us that if I were to go close to these objects, that space and time would be distorted in this bizarre way that Einstein's theory predicts. That there would be this horizon, the surface of a black hole, that's like a one-way membrane. If I were to cross inside, I could never get back out. And it really is like the Harris cartoon, right? We're in the stage of, it's black, it's a hole, and I'd say it's a black hole. I mean, not much better than that. So what we needed was some kind of a signal to come to us from deep in the gravitational field of the black hole and tell us directly that there's a black hole there with these bizarre properties. Right? So that's been like the holy grail, what theorists and experimenters have been trying to find. All right, let me talk a little bit about gravitational waves. So this ripple of curvature in space and time propagates out. By the time it gets to us, say at the Earth, it's very, very weak. But let's not worry about that for the moment. What would its effect be? How would I go about designing a detector? So imagine another thought experiment. I arrange a ring of particles like this, and these are special particles. They don't interact with anything except gravity. Right? So I don't have to worry about electromagnetic forces on them or anything like that. They only respond if gravity comes by. And then a gravitational wave comes along, and what it does is it will stretch the space between, say, two ends of a diameter, move these two particles apart, while at the same time squeezing the two that are 90 degrees away from them. And then half a cycle later in the wave, this direction will be squeezed and this direction will be stretched. So that's what this little graphic is showing here. And for the experts in the audience, there are two polarization states. That just means I can think of waves as two independent sort of modes of propagation, and they travel basically at 45 degrees to each other. The amount of this distortion depends upon the strength of the wave. The stronger the wave, the bigger the distortion. And so the way we measure it, and this is the only equation I'm going to show tonight, right? So the effect on the detector, so we'll call the amplitude, how strong the wave is, h, and it's just the fractional change in the distance between the two particles. So if the undisturbed circle had a diameter L, and then when the wave comes by, you stretch by delta L, and you take that fraction, and that's the strength of the wave. That's h. So to design a gravitational wave detector, what you need is some analog of these two particles, and maybe two in this direction, and then a way to measure the change in the length. Okay, now here's how it's actually been done. So this is the LIGO. LIGO stands for Laser Interferometer Gravitational Wave Detector, Gravitational Wave Observatory, sorry. And this is in Hanford in the state of Washington. And you'll see this long pipe. This is about 2.5 miles, and it's an L shape. Inside this concrete pipe, is a steel tube. The steel tube is about that wide, and it's a high vacuum, and laser beams are shot down towards the end here, and then there's a mirror that hangs from a suspension, and it bounces the beam back, and similarly down the other arm, and these come together in this corner station. They're combined, and the eye, the interferometer, that just means that what you're doing is when you combine the laser waves, if the wave from the one arm is, say, at a peak, and the wave from the other arm is at a trough, then they cancel each other, and there's no light. It's actually dark right at where you're observing. On the other hand, if the peak of one wave coincides with the peak of the other, then you get a peak that's twice as high, and you get a strong, bright signal at that point. Now suppose that a gravitational wave comes by. Well, we know what happens, right? The one arm stretches and the other arm squeezes. We're changing the length, the distance that the laser beam travels. And so if we had arranged things where, say, a peak and a trough were exactly canceling each other, when the wave comes by, we've changed the length, the distance that the light has to travel. And so the number of wavelengths will have changed in that distance, and so they'll no longer exactly cancel. You'll see some light. And you could now go out and build a gravitational wave detector. I've told you the secret, right? Okay, the problem is the effect by the time the wave reaches the Earth is extremely small. How small? So this big collaboration of people that's involved in this experiment, they set out to measure a change over this 2.5 miles of a distance 1/1000th the diameter, not of an atom, but of a proton in an atom. Another way to think about it, that's like measuring the distance between the Earth and the nearest star, 4 light years away, to the precision of the width of a human hair. It's unbelievable, okay? It's a miracle, really is. Now, of course, if they were to report that they had measured such an effect, nobody would believe them. They would say, oh, come on, somebody slammed the car door in the parking lot. Whatever, right? So they built another one. This is in Livingston, Louisiana, about 2,000 miles away from Hanford. And it's an identical layout. And the idea is if you can see the same signal at these two places, and you see it at the same time to within the light travel time between the two detectors, so within a few milliseconds, if you see the same signal within a few milliseconds, you can be pretty sure that what you're seeing is not some signal generated on the Earth. It's something extraterrestrial, something astrophysical that has arrived at your detector. So the LIGO project has been quite a long thing. They built the initial detector, they installed some early interferometers, they made sure it was all working, and then they did an upgrade to try to get to the sensitivity where they believed they should see signals. And so the upgrade was completed in 2015. The first science run started in September 2015. And so probably over the next 3 to 5 years, the sensitivity will improve by yet another factor of 3. Now, to give you a sense, this is a plot of the distribution of galaxies in our sort of local neighborhood of the universe. So the Earth is at the center right there where it belongs. And this small little sphere, that was the range of the initial LIGO experiment. And this is the planned range, the reach of it, for when the upgrade is completed. So right now, the range is somewhere out here, and about a factor of 3 to go to get out to here. This, by the way, is drawn for what they all expected they would see, which would be the collision from two neutron stars. That was the anticipated most likely event that they would see first. So by the way, you can see from this picture that if you increase the range by a factor of 10, whoops, sorry, back on that. If you increase the range by a factor of 10, the volume of the sphere gets bigger. Who knows the answer? A factor of 1,000, right? You remember your high school geometry, right? The volume of a sphere is proportional to the radius cubed. So 1,000 times the event rate. So that means if there was something that was only going to happen once every 1,000 years, you'll now see it roughly once a year. Okay, so that's why everybody was very excited about this potential increase. All right, so now let me talk about something that I've been involved in, this computer simulation idea. Traditionally, we divide physics up into theory and experiment. And since there's so much specialization, we even have people who only do theory and only do experiment. Computer simulation is this idea that instead of doing a real experiment with, taking two black holes and smashing them together in your backyard and seeing what happens, you do it on a computer, but you use the theory to tell you the rules, how you should actually carry out the calculation. So it's kind of in between. And this is a widely used technique now in all areas of science and engineering. So for example, in the old days when an airplane was designed, the engineers would build a wind tunnel, and they would take, say, the wing, or a scale model of the wing, put it in the tunnel, blow air over it at high speed, and measure the lift and so on to make sure that the plane would actually fly when you got in it. Nowadays, what people do is they take the equations that describe the flow of air, it's the fluid flow equations, they program them on a computer, they take a model of the airplane, they lay out a little grid of points where they can actually calculate, using the equations of fluid flow, what the lift and the drag and so on on the plane will be. And provided they have a fine enough mesh of points, they can do the calculation to sufficient accuracy that Boeing's willing to spend a few $100 million to actually build the plane. So those of you who've been on a Boeing 787 Dreamliner, that plane was never tested in a wind tunnel. It was completely built after computer simulations. Okay? All right, so now let's get back to waves from black holes. So imagine you have two black holes that are orbiting each other. This is the pebble in the pond. It's a disturbance of space and time, and waves are produced. And that's sort of what's shown in this part of the diagram. Then there's this very complicated merger where you end up with a single black hole, and this single black hole kind of oscillates a bit, and it radiates some waves which gradually die away, and then you end up with a quiescent black hole. Now, this first part of the calculation, when the black holes are quite far apart, gravity is relatively weak, and so we can use Newtonian theory with just some small corrections for the strong gravity. And so we actually know how to calculate this even without computers. So that's why this part is called known. This end part, where you have small deviations from a quiescent black hole, that's also known with pencil and paper. In fact, my PhD thesis was to work out how to calculate this. But this middle part, where nothing is simple, you have strong gravity, violent black holes traveling at half the speed of light, merging, making a single black hole, there's no hope of calculating that, and that's where you need the computers. And so this field of numerical relativity, which has been in existence for essentially as long as people have been using computers, the challenge, well, this was like the Holy Grail problem from a theorist's point of view, that if you could detect these signals, then you could finally confront the theory with the experiment in this sort of very dramatic strong field regime. Okay, so it's just like the Boeing 787. You start with two black holes in orbit. You set up a grid of points, as many grid points as you're willing to pay for computer time. You record the values of the gravity, the curvature of space and time at each point. You then choose a little time step, and you use Einstein's equations to tell you how the gravitational field changes to get the next time step. And then you just keep doing this, okay? And then you can carry out the whole simulation on the computer and predict the signal. Now, why would you want to do this? Why is this useful for LIGO? So there are two reasons. One is it's the needle in a haystack problem, right? It's hard enough to find a needle in a haystack, but it's a lot easier if you know what a needle looks like. And so the idea here is you're trying to measure this very weak signal, but if you can predict what the waveform actually looks like, you can try to look for that particular signal in the data that's coming in. And if you find a match, then you can say, aha, I know what that is. Now, in order to do this, you have to do this for all different values of masses and also the spins, the angular momentum that the black holes can have. So these two colors, the black and the red, those are those two polarization states of the waves that I was talking about earlier. But you can see for this case, where the one black hole is much bigger than the other, and it has spin, and the spins are pointing in weird directions, you get quite a complicated shape here. So you can turn it around. If you could measure this, then you could deduce what the signal came from, what the source was. So that's the second reason, to be able to measure the properties of the source. So we have a collaboration called SXS Collaboration, simulating extreme spacetimes. And it started with my group in Cornell, and then unfortunately graduate students have this annoying habit of graduating and moving to other places. So by now there are about 30 people work all over the world. This is just a handful of people who are members of the collaboration, all working together on not just these black hole problems, but also looking ahead to the neutron star discoveries that we expect will happen very soon. And so, here's one of our early results, a very simple case. You take two black holes of the same mass, no spin. This shows them orbiting around each other and merging, and you get this waveform, which you see is much simpler than the one I showed earlier, because this is a boring, equal mass kind of case. What's plotted here, never mind the fancy mathematics here, this is just the stretching and squeezing of the wave. Okay, and then this was a more realistic case, a more difficult one, the one that I showed earlier. Okay, so I'm sorry, I'm going to show you a movie. I have to unfortunately go to my computer here. Okay, so this shows this case of one black hole 6 times the mass of the other. They're orbiting each other. The color coding just encodes the fact that the black holes actually have spin. And the first thing you notice is that the orbits, unlike the orbits of planets in the solar system, where Newtonian gravity is a very good approximation, the solar system planets, they stay in the same plane. Here, because of the spin, that vortex-like effect of the spin of the holes on the gravity, drags the orbits, we say the orbits precess, around each other like this, in this very complicated pattern. And then we slowed down the calculation so you can see the black holes actually merge. I love that part. It's just like a kiss. Okay, so this, you should remember, is not an artist's impression, right? This is the result of a real supercomputer calculation. Everything of that in this image has been actually calculated by solving Einstein's equations, and then we just make a visual representation after the fact. Okay, so here we get to the big discovery, right? So this was the New York Times on February 11th last year, and you can see cosmic chirp from black holes colliding vindicates Einstein. And you'll notice this image. I'll come back to that in a little while. I'm sure many of you have already seen it. And all over the world, headlines. This was the notice board in the LIGO lab headquarters at Caltech, and you can see they've put up newspapers from all over the world. So what actually happened? So I don't know if you can see the two black holes here, but about 1 billion years ago, these two black holes were orbiting each other, and they'd gotten sufficiently close. Here you can see the gravitational waves traveling out like the ripples on a pond. The red and the blue is supposed to show which parts of space and time are stretching and which are squeezing. So this traveled across the cosmos, right? Kept going. About 70,000 years ago, the waves arrived at our galaxy. So by now, the spherical pattern had stretched out to an enormous radius. So on the scale of our galaxy, the waves just looked like they were straight, right? Because the curvature is negligible on this scale. I'll let you think about how did I get hold of this picture of our galaxy? The waves actually arrived first in the southern hemisphere, traveled up all the way through the Earth. The gravity is so weak, that's what makes it such a challenge to detect. It's virtually unaffected by traveling through the matter of the Earth. Arrived first at the detector at Livingston, and then a few milliseconds later arrived at Hanford. This is inside, this is the corner station at Hanford. You can see this is one of the steel pipes going out this way, and in the back there is the one going out that way. This is inside the corner station. As you can see, this sort of reddish thing that's hanging here is one of the mirrors in that corner station. And so it changed the length, the relative length of this arm by this tiny amount. And this is what showed up on the control panel at the two observatories. So this is time. You can see the whole signal lasts just a few tenths of a second. And this is frequency. And you can see that the signal, the color shows stronger amplitude. As time goes on, the frequency goes up and the intensity goes up. And that's what we saw, that's what we expect from two black holes, two objects that are spiraling in. So as they get closer together, they go faster and faster, the frequency goes up, and the strength of the signal goes up. And then after the detection was made, there was a sort of period of data analysis. And this is from the discovery paper in Physical Review Letters. And it shows up here sort of the actual waveform that's observed. Okay, so there was no need for needle in a haystack. I mean, this signal was so strong that you can actually see it above the, this is probably noise over here. It's a strong signal. And you can see how the amplitude is sort of increasing. And then over here, what's been done is to take the signal at Livingston and superpose it on the one at Hanford, just offset it in time so that, that they match up. And again, you don't need any fancy statistics, right? You can look at this, and it's the same signal. Now, what's shown down here is in gray, they've taken the signal and broadened it a bit to represent the uncertainty in the measurement, right? There's a little bit of error whenever they make a measurement, and that's the error in the measurement. And then shown superposed on that is the red, the numerical relativity. That's from our SXS Collaboration, calculated this waveform and show, I mean, again, you don't need fancy statistics. You can look at this and see that it's a match. And so the way I like to say this is this panel here tells us the experimenters detected gravitational waves. At the same time that they're monitoring this change in arm length that's being plotted over here, they monitor all kinds, thousands of environmental variables, seismic noise, wind, barometric pressure. I can't even remember what all the things they monitor. There were no anomalies, no signals in anything else. The only thing that was detected was this. So we know that they detected gravitational waves. What this tells us is, what did the waves come from? They came from two black holes that were orbiting each other and that merged. And you know, when I first learned of this discovery and sort of saw this picture, I mean, I went numb for a few minutes, because you try to wrap your mind around this. I mean, this bizarre prediction made, this theory, it's been here for 100 years, all these thousands of people working on this incredible experiment. They make this incredible measurement, a bunch of other people working on the theory, trying to calculate, wrap your mind around black holes out there, 30 solar masses each, smashed together, producing this, and it agrees. It's just I don't know what I don't have words to describe this. This appeared. This is the statue of Einstein outside the National Academy of Sciences in Washington, and I think that that sums it up. Except, of course, as I said, if you want to be historically accurate, Einstein actually didn't believe that black holes would ever occur in nature. But still, we've got so much else right, we'll overlook that. And then a few months later, there was a second event. Okay, this one you can see has many more cycles. So from that we can tell that the masses of the black holes are actually a bit smaller, so that they're further apart when their frequency matches up to what the experiment can actually detect. And so you actually have many more orbits around each other before they finally merge. But basically, it's the same kind of phenomenon. Okay, so there's no doubt these really exist. So right now, so after this, the detector was shut down. There was some further work, part of the upgrades, and now there's another observing run going on right now, which will end sometime in August. And presumably very soon there will be more papers about whatever the latest measurements are. Okay, so I'm going to end by showing you one more movie. All right, and so this is this movie which shows the two black holes orbiting each other against an imaginary background, but they're real stars from a star catalog. And the calculation is what you would see with your eyes or with a telescope. So light rays have been traced from every star to the viewer. And the light rays that travel close to the black holes feel the gravity of the black holes, and the light rays actually get bent. So that means that when you look back along the light ray that reaches your eye, that even if the actual star was over there, you see it displaced because the light ray got bent and comes to you from a different angle. And all the sort of dancing around of the stars, all that sort of jittery motion that you saw, that's because the black holes are not at rest, but they were actually orbiting. And so you'll see sort of some of the stars appear to move around. It's just their light rays being deflected. Sure. And some of you may be able to see on the black holes their little eyebrows, their little shadow. So what you're seeing, you're seeing the black holes as shadows, right? Because those are light rays where if you trace back from your eye, those light rays, instead of ending up on a star that you can see, they actually end up in a black hole. So nothing comes out, you see black. Those little eyebrows were from light rays that when you trace them back, the gravity of the black hole is so strong that it deflects the light ray all the way around the black hole, and then only does it get captured. And so you see a sort of that small little region where that is true. And if we could zoom in again, you'd see actually the eyebrows have eyebrows where you go around twice before you get together. So what I want to emphasize is this is not this is a real, everything here is a real calculation. So first of all, the simulation that produced the two black holes orbiting each other, and then tracing the light rays, including putting in the redshift effects, because as the light rays come to you, they pass close to the black hole, right? And remember, we already discussed how time, the ticking rate of time changes as you go into the strong gravity, and that's related to the frequency of the light. So you see this redshift, and because the black holes move, when the light ray climbs out of the black hole's pull and comes to your eye, the effect is not symmetrical. It doesn't cancel. So you get a distortion in the colors of the stars as well. And then all the lensing effects in these peculiar way that the images move around. Everything is a calculation. And it's remarkable, again, to me, how it's taken 100 years, but basically we're at the stage of being able to do these calculations and the double bonus of having the experiment to confront the theory with. And who knows, maybe 100 years from now, our observational prowess will have reached the stage where there will actually be observations that look like this. Thank you. Yes.
So we have two microphones. I think I see one here and one over there. And Saul has been gracious enough to take questions. So we'll let people stretch their legs and ask questions. I can just say that for those of you who haven't realized, this is really, for most of us, a sort of a once-in-a-lifetime discovery. And it really brings me great pleasure to bring this to everybody here. Looks like we have a question. Please.
I was curious, you showed when the detectors found those waves, you did a simulation that matched. how did you know what to simulate? There's so many different masses and spins.
Yeah, what the experimenters actually do is they build up a template bank. So they have hundreds of thousands of waveforms which have been produced by theoretical modeling, which they use the numerical simulation. We can't do hundreds of thousands. These are just too big. I mean, a typical calculation takes a month of supercomputer time on one of the big national machines. So we can only do a much smaller number, but they calibrate the templates against the numerical calculations. So we had a pretty good idea from which templates, they tried all the templates and found, told us which ones fit very well. So we had a pretty good idea of what masses and spins to use. And then we did a couple hundred calculations, bunched around those values, and then that was just one of them.
Cool. Can I do one follow-up? The time scales that you were talking about, is that a time scale just right at the very
It's right at the very end, yeah. So when these black holes are further apart, they could take hundreds of millions of years to spiral in. It's just the last part. So the LIGO detector is only sensitive when the frequency of the waves is greater than about 10 or 20 hertz, 10 or 20 cycles per second. And so you have to wait until that last little bit.
Yeah. All right. Thank you.
I have a couple of questions.
Yes.
The first one, are these gravitational waves affected by anything along its path, like something like black hole, for example? And my second question is, if there are multiple of these orbiting black holes or any black hole which has angular momentum, so what we get here on Earth will be the superposition of all these things. So how do we actually separate and identify where exactly these black holes are?
Right. So very good question. So the first question is the wave affected as it travels through the universe? So most of the universe is actually pretty transparent to gravitational waves, right? So, occasionally there's a star in the way, but you saw, even for the Earth, I mean, the interaction of the gravity with matter is so weak. I mean, we're used to thinking of gravity as strong, right? I mean, we can only jump a few feet in the air. But I mean, if you just take, an ordinary toy magnet, you can lift, a metal disc quite easily against the whole gravitational attraction of the Earth. Okay, so gravity is weak compared with other things, and it manifests itself in that way. Of course, if there was a black hole in the way, that would absorb the gravitational wave. But along any given line of sight, the black holes are pretty small. It doesn't do anything. Then let's see. The other question was.
So there could be some multiple sources of gravitational waves.
So you might have black holes merging, at different time all over, and we're bathed in the sea of gravitational waves. So part of the LIGO experiment is actually to try to detect that. That we call that a stochastic background. That's just the fancy jargon for superposing a bunch of signals where any individual signal is too weak to be picked out. But if you have many, many of them on top of each other, you can hope to see some kind of an effect. The effect from that is not this nice waveform that we saw. It's a more subtle way that those have to be detected. But they don't interfere with the ability to detect. This is a relatively strong signal that sticks up above the level of that background.
Thank you.
Yeah. Knowing what you know, with the help of computers, etc., do you ever contemplate what Einstein could possibly have had going in his brain, that he could have thought all this through?
Yeah. I've thought about that a lot, right? Every physicist thinks, I want to be the next Einstein, right? So I think if you look at Einstein's path, there are a few things that stand out. One is he wanted to understand and work out everything for himself. He did badly in college partly because he wouldn't show up for exams and things like that, because he felt that he was being taught the old physics, not the new stuff. And he was being taught it in a way that was unsatisfying. And so he spent a lot of time rethinking these things. I mean, how could you come up with something like time is relative to, most of us are pretty accepting, we go to school and they tell us, time, it's, you start reading a clock and then you go, maybe you do some science experiments and you keep time and so on. We don't even think about it, but he thought about it. And I think it's that kind of questioning, of almost a questioning of authority, not being satisfied unless you understand it yourself. I think that's the hallmark of the very best scientists.
Well, the second thing is for you to take your brilliance so candidly, so effortlessly, when all of us are in awe of what you say and what you've done, etc. And I might just take issue with one little thing. Yeah. I think the statue of Einstein belongs in front of the White House, not in front of the Academy.
I was personally wondering, and I'm sure a couple other people are wondering this as well, in the side-by-side comparison of the two color graphs of the detections, not the waveform, but the color graphs, why was the one in Washington, I think, considerably brighter than the one in Louisiana?
Yeah. So I don't really know the answer. In other words, was it just the settings on their thing, the way it was done, or was it a real effect? The detectors actually have slightly different sensitivities at any given time, because it depends on, they are affected by the local background noise to some extent. So I don't know whether it was that reason or whether it was just the way, the settings on those particular pictures. I actually don't know the answer.
Okay. And how long do you think it's going to be until we have the, sort of holy grail gravitational wave detector in space?
Yes, so gravitational wave detector in space is a big dream, because it would first of all, it would allow us, LIGO is sensitive to black holes of masses like the ones that were detected, 10 or 30 solar masses, somewhere, in that range, say 1 to maybe 100 or a few hundred solar masses. But we believe at the centers of galaxies there are these supermassive black holes, somewhere maybe 1 million or even 1 billion times the mass of the sun. And in order the wavelengths or the frequencies of those are so low that there's no hope of measuring them on Earth. There's just too much noise in ground motion and so on. So there's been this dream of putting detectors in space. You'd have satellites, maybe an equilateral triangle with the laser beams bouncing back and forth. But now you'd have arm lengths of maybe 500,000 miles or something like that, and try to do this. Anytime you do things in space, there's a big dollar factor. We're talking, several billions probably. There was a plan to do this in 2034. Because of the excitement of this discovery, it's been moved up. We're now hoping maybe like 2029. Unfortunately, the U.S. is not a major player in this because various, just budget problems in Washington. There isn't really money. It's the European Space Agency that's leading the effort on this. The NASA has now proposed to restart the U.S. effort on this program, and we're hoping that will lead to something. There's also talk, apparently the Chinese government is very interested in doing this, and maybe that will spur Washington when nothing else will.
Thank you.
Hello. I was wondering if all black holes are going to look exactly like a 360-degree circle, and if there's any way to to detect the effects of black holes before they affect us?
Right. So usually when physicists draw the black hole as a 360-degree circle, that's usually because we're representing a non-spinning black hole. So we would expect it to be spherical. If the black hole has spin, then the geometry is not spherical. It's, as you would expect, there's sort of an oblateness. So I don't know if you noticed some of the early pictures. I drew them as kind of these ovoid kind of shapes. We actually have precise mathematical descriptions for that geometry, what the shape actually is, at least for the quiescent black holes when they're just sitting there. As to can we infer the presence of black holes when they're not smashing together and sending out waves? Well, so that's what the poor astronomers have been doing, for the past 30, 40 years, finding these places where, for example, there'll be a star which you can observe from the optical or X-ray light that comes off it. And we know it's in a binary system because we can see its spectral lines, and we can see the alternating red and blue shift as the star comes towards us and then goes away from us, comes to and right. So we know it's going around something, and there's nothing there. We don't see anything. And then from the orbit, we use Kepler's laws, and we can infer the mass of the object that we don't see. And there are about a couple dozen cases where the mass of the object that's not seen is too big, if Einstein is correct, it's too big to be a neutron star. And so those are the cases where we've inferred the existence of a black hole, right, which I said too much mass in a small volume. But as for directly imaging it or something like that, that's much more difficult. There is actually a project called the Einstein Telescope, which hopes to actually try to image, say, the black hole at the center of our galaxy, to see the shadow by doing ultra-high resolution imaging against the background. And that's something for the next perhaps 10 or 15 years. We'll see.
Thank you so much.
There's the time differential shown between the two detector arrays.
Yes.
If theoretically you put in a third detector array and use the time differential, could you get an idea where?
Yes, great question. So in fact, even from the two detectors, you get a circle on the sky where you can infer where the source was coming from. And by using, there's actually some slight difference in the alignment of the two detectors from the different polarizations. You can even get some more probability, different parts of the circle and so on. Having more detectors gives you more sky localization. And LIGO has a bunch of partners, astronomers, with telescopes of various kinds, radio, optical, X-ray, and so on. And what happens is every time LIGO has a potential detection, they call it a trigger to distinguish it from a real detection, something which might be a signal, they immediately send out a message to these partners saying, there's something, and they give this sort of band on the sky, and then people can look and see if they can see any kind of counterpart. The localization with the current detectors is not very good at all. I mean, there's lots and lots of stuff in that region. But a little later this year, a detector in Italy, which is an Italian-French collaboration, it's called Virgo, will come online. It will join this collaboration. With 3 detectors, as you say, you already get much better localization. There's a Japanese detector called Kagra, which is being built. It will come online probably, I don't know, maybe 5 years from now, 6 years from now. And most recently announced is another detector in India, which will probably come online maybe 7, 8 years, optimistically, from now. And so the hope is that in the 2020s there will be this global network, and we'll do real astronomy with these
It's wonderful. Kind of what other question is, how much approximately do these detector arrays cost? I mean, it's like it's a regular
so the only one I know prices for is LIGO. So for LIGO, the construction cost was $300 million in 1995 or so. The running costs are about $20 million a year. So you can do the arithmetic, per site, sorry. Yes, that's why he's a director of an institute. He's good with the budgets. And then, things like the upgrade, that's, extras and so on. So by the time you add it all up, over a 20-25 year period, you're talking about $1 billion.
Hi, this is a random question. I have under the understanding that in the last year, a black hole, they feel there's a digital imprint left on the horizon when something enters it. If you were to throw your wallet, it would duplicate it into a binomial code on the horizon, and the object goes in, and then that gets compacted. Is that, how do you feel about that?
So this is very speculative stuff. You're now, I won't even say at the frontier, you're beyond the frontier, right? So what motivates these kind of speculations is you can blame Stephen Hawking. So Hawking showed that so one thing that's missing from Einstein's theory is quantum mechanics. And we don't have a complete quantum theory of gravity. But there have been some calculations where it's sort of you partially put quantum mechanics together with general relativity, and Hawking did one of these calculations and showed that black holes are actually not perfectly black. That if you include quantum mechanical effects, there is a small amount of radiation that comes out of the black hole. It's almost like it has a temperature. And for astrophysical black holes, things like we're talking about here, is completely negligible. There's no hope of ever measuring. The temperature is infinitesimal, much smaller than the microwave background rate. It's just a purely of theoretical interest. If somehow you had tiny black holes, you might actually be able to see something. But from a conceptual point of view, this raises a problem, because as this black hole is radiating, it loses energy, so it's losing mass. And so it shrinks in size. And eventually, all the mass has been radiated away. And then the question is, what are you left with? Because according to general relativity, inside the black hole, there's a singularity. What does that mean? That just means it's some region where the curvature of space and time has gotten so extreme. It's like in high school when you're divided by zero, and your teacher would come and rap you on the knuckles, right? Something is broken down. The theory no longer applies. So people have been struggling to try to try to have a complete understanding of what's going on. What happens to all that information that went down the black hole and now is being radiated away? According to quantum mechanics, you can never lose all of that information. But here, you form the black hole, and then this radiation comes out, and it's just like a temperature. There's no memory of how the black hole was made. And so people who believe that somehow that information must be imprinted, there have been all kinds of crazy, I should be polite, right? Some of these proposals come from KITP. Some interesting proposals have been made about how the black hole remembers that information, but we don't know whether any of that's correct.
Appreciate that.
Great presentation. I was interested in the simulating model. How many cells did you have in that?
So the calculation that I showed actually has not too many cells. It's quite modest. It's something like 75 along each dimension. The reason we could get away with such a small number is we use a fancy numerical method. And our competitors, there are about 10 groups around the world who do this. they all use a different numerical method, and they need to use hundreds of points along each dimension, and so that's why we do a better job.
How many calculations does it take to?
So even for us, the easy cases take about a week of supercomputer time. The harder cases take a month or two.
So the lights dim. Right?
Yeah.
Please, final question.
Thank you very much for a wonderful presentation. And I just want to make a comment. I expected everyone here to be an Einstein aficionado, and I spoke with at least a dozen people before it started, and not one knew that right now National Geographic, there's a series put on by Ron Howard all about Einstein, and it's called Genius, and it's every Tuesday at 9 p.m. And I wrote a review on it in the Montecito Journal. If you pick up this week's edition, on page 8, it says it's all about time. Thank you very much.
Thank you. All right, thank you, everyone. We'll expect to see only about a quarter of you at the Cafe KITP. Thank you very much. Thank you, Saul.